Good morning. Welcome back to the Blackboard. We are gonna continue on with the Eigenvalues, Eigenvector chapter, and more importantly, we're gonna now find the eigenvalues and eigenvectors. If we recall from last video, we just had to show that the eigenvalues and eigenvectors that were given to us were part of a matrix. In this video, we will look at the steps in finding those vectors and values. So for this one, we have 4 examples, although I'm only going to be doing one and try to go with much detail as I can. And then the other 3 will be at a separate video, and that one kind of be like much more quicker and more likely than not just skip some steps since it's just pretty much doing the same thing. So we're just gonna go ahead and do part A, and then we'll finish the rest of this example on another video. So let's get started. So our first matrix is a 2x2 matrix with 6, -3, -2, and 1. And so if you recall from lecture, to find the eigenvalues, you have to set the determinant equal to 0. Well, the determinant of the matrix minus lambda I. Oh, which, yeah, another thing I need to let you know. So during lecture, I did mention that to find the characteristic equation, it's you take the determinant of lambda I minus A and set that equal to 0. There is another way to do it, and I feel like this one is a little bit more work because you have to take the entire matrix and turn it to, or just flip the signs. But another way you can do it is just have A minus lambda I. Take that determinant and set it equal to 0. So that way you're only working with the diagonals. And so we're just going to go ahead and use this form. And so what we're going to do is just pretty much have 6 minus lambda. And then this would be -3, -2, and then 1 minus lambda. Set that equal to 0. And so now we're just gonna, if you recall, like earlier in the topic, we discussed about determinants of a 2x2. So you just multiply it out. 1 minus lambda minus 6 times, well, -2 times -3 is 6. So let's just say it's the same, it's equal to 0. We're going to expand, and so we are left with lambda squared minus 7 lambda plus 6 minus 6 is equal to 0. So obviously this 6 will cancel out. We can also factor out a lambda. So this will just be equal to lambda times lambda minus 7. Set that equal to 0. And so we see that our eigenvalues is lambda is equal to 0 and 7. And so that's how you find the eigenvalues for pretty much all the matrices. There will be some that will have a characteristic equation, but there's ways to work around it. And so now we are going to find the eigenvectors of the corresponding eigenvalues. And so to do that, we just plug in lambda, or we just plug in our eigenvalues. So when lambda is equal to 0, we get that our matrix becomes 6 minus 0, it's just 6. These stay the same, you have 1 minus 0, it's just 1. And so that will be our matrix. And now we have to put this in row reduced echelon form because we know that it is going to be multiplied by some eigenvalue, or not eigenvalue, eigenvector, and it's going to have to be equal to 0. So this pretty much becomes like a system of equations where we have to put this in row reduced echelon form. You can also put it in augmented matrix if you feel comfortable. I'm gonna do it here for now, but I typically don't do that, mostly because we're just going to be working with zeros on the right side, so nothing's going to really change. And so what we can do now is we can see that the first and second row are a multiple of each other, and so this can be turned into 6. Well, this can just go to 0, 0. This be 2, 1, 0, 0. We can move the 2's on the top, and so we're just left with -2, 1, 0, 0, 0, 0. And if you remember how to find your solutions, it's just x1, x2 is equal to, take it back, -2x1 plus x2 is equal to 0, and then this makes x1 equal to x2 over 2, and so your solution just pretty much becomes -2, 0 plus t, and then this would be 1/2 1. And so your eigenvector will be the kernel of the solution, which in this case it will be this portion here. And so our first eigenvector will be x 1/2 1. And if you remember I think I mentioned in the lecture, if you remember in the lecture that once when you find one eigenvector, if you multiply by any constant, that new eigenvector will also correspond from the eigenvalue. And so what we can do here is we could just multiply both sides by 2, so we can get rid of the 1/2, and so we are left with our eigenvector being 1, 2. And so now we finished with our first one, so now we have to plug in the second eigenvalue, which would be when lambda is equal to 7. And so we'll get is 6 minus 7, which would be -1, then -3, -2, and so we have 1 minus 7, which would be -6. And like I mentioned, like using this way, using the not lambda, the a minus lambda I method, it makes it so much simpler because all you have to do is manipulate the diagonals. Everything else stays the same. If it was the other way around, then this would the 3 and 2 will have to change signs, which at some point you'll start forgetting to do that. So I just like using this one. And then again, we have two values, and which when they multiply to each other will be 0, 0. And so we're gonna have to find the solutions. So it'll be -1, -3, -2, -6. And then on the right side will be 0. Again, these first and second row are multiples of each other, so it is a multiple of 2 actually. And so we can just completely get rid of the bottom part, and so we'll have 0, 0. And then now we'll have, that's pretty much our row reduced echelon form. So we'll have -x1 minus 3x2 is equal to 0, and we can just find x1, so x1 will just be -3x2, and well, actually take that back, we can get rid of the negatives here. This will be 1, 3, So we'll have x1 is not equal, plus 3x2 is equal to 0. So you have x1 is equal to negative 3x2. And so we will have the solution x1 x2 is equal to 1 0 plus t negative 3 1. And then obviously our eigenvector will be what's in the kernel, and this will always be true. It's whatever it's in the kernel or nullity, that will be our eigenvector. And so our second one will just be, we're not going to manipulate this one because it's pretty much whole numbers. And so that's pretty much our answer. It is lambda is equal to 0 with the vector, well, it's supposed to be x1, but 1 2, and lambda is equal to 7 with the corresponding eigenvector equaling negative 3 1. And so that's pretty much it in finding the eigenvalues and eigenvectors. This was, like I said, this usually supposed to take a little bit less time, but I kind of want to go through every single step. And so yeah, I'll see you guys in the next video where we'll finish up the other 3 examples, and after that we'll have probably one long example with a 3x3 matrix. So yeah, I'll see you guys in the next video.